Okay, so this is a short video meant to make up for the double snow delay that we've had in Gen Chem 2. So I'm going to go through a few new equations and how to use them. And I'm going to have some practice problems in here, just like some of the other previous common gas law videos. And if you're still feeling a little lost, be sure to reach out via email or come to office hours. And also know that we will be doing some more of these types of problems on our in-class problem day in a couple weeks. All right, so let's get started. So up until this point, there's one variable that we've been consistently ignoring, right? And that is the quantity or number of particles or moles of gas in our practice problems and our hypothetical situations, right? So up until this point, we've been mathematically ignoring moles or quantity of gas. So we're going to quickly cover the last law that deals with this, right? So Avogadro's law states that at standard temperature and pressure, which again is 1 atmosphere of pressure and 25 degrees Celsius or 298.15 Kelvin, 1 mole of an ideal gas will take up 22.4 liters. So this is what we define as our standard molar volume, right? So what might you expect to do? What might you expect a balloon to do if you doubled the number of gas particles in it, right? If 1 mole takes up 22.4 liters, just no matter what type of gas it is or which gas it is, you can reliably assume that the volume of that balloon is going to double, right? So Avogadro's law says there's a direct relationship between the number of gas particles and the volume a sample will occupy. And mathematically, we discuss this as V1 over N1 equals V2 over N2, right? So the initial volume of something divided by the number of moles of gas will equal the second volume divided by the second number of moles. Okay, so hopefully everyone realizes that there are in fact some things that are different between gases, right? Up until now, the common gas laws and the ideal gas law, we assume that all gases behave identically or behave the same under ideal conditions. But hopefully everyone knows that the density of gases is different between types of gas, right? The density of hydrogen gas is not the same as the density of diatomic nitrogen or diatomic chlorine, right? They have different masses and take up different volumes. So even if we assume that all gases take up 22.4 liters at STP, we know the masses of those gases will be different, right? Hydrogen has a lot less mass than diatomic chlorine, for example. So we can actually use Pipner, the ideal gas law, to determine something about the density of a gas if we are given enough information, right? So I'm going to walk you through mathematically how we do that, and we'll arrive at a new equation / way to use the ideal gas law. So we know that density equals mass divided by volume. We know that our ideal gas law, right? Pressure times volume equals the number of moles of our gas times constant R times temperature in Kelvin. If we arrange both of these formulas to solve for volume, we get volume equals mass divided by density, and then volume equals nRT over P. If we then set those equations equal to each other, right, volume equals volume, and cross multiply, we will get mass times pressure divided by our N times R times T will actually equal the density of our gas. Right, so density equals mass times pressure divided by nRT. We can take this one step further actually. If we take out or separate mass divided by the number of moles of a gas, we now have the mass of a gas divided by the moles of gas times P over nRT still equals density. And hopefully, mass over N seems familiar to most of you, and that's because what we've done here is actually mathematically removed the molar mass of our gas, right? So if we know the molar mass of our gas, say for hydrogen, which is roughly 2.001, we can include that constant into this method of using the ideal gas law. Right, so the takeaway here is density equals the molar mass of your gas times pressure divided by nRT. There should be an N here. And that can allow you, again, to use that ideal gas law in a few different ways. All right, now that we've rearranged our ideal gas law, or really changed up its utility by adding a little extra information, let's do a practice problem, right? So we're going to ask the question, at standard temperature and pressure, what is the density of nitrogen gas? And if it's been a while since you've thought about a diatomic nitrogen gas, remember it's just two nitrogen atoms bonded together with a triple covalent bond. And its molecular mass, again, is 28.01 grams per mole. So we begin by setting up our problem here. And it looks like I'm going to have to just scroll. So the first thing to remember, right, standard temperature and pressure is 1 atmosphere of pressure, and our temperature is 25 degrees Celsius, which rearranges to 298.15 Kelvin. So we'll just jump right into using this for our practice problem. Right, so remember, density equals the molecular mass of our gas, which is going to be 28.01 grams nitrogen divided by 1 mole of nitrogen. And then we're going to continue to scroll over, right? And so that's going to be P over RT, right? So 1 atmosphere of pressure divided by 0.0821 liters times atmospheres over moles per Kelvin. So because our external pressure is in atmospheres, it makes the most sense to use this this form of our R constant, right? And then we're going to multiply that by 298.15 Kelvin in the denominator. So if we keep moving along, right, our atmospheres cancel, our kelvins cancel. I'm going to rearrange things here. So if we rearrange things, now that comes down to 1.25 grams of nitrogen per 1 liter nitrogen, right? I skipped over the part where the moles cancel, but we have a denominator of a denominator that's going to cancel out with the denominator of our numerator over here. Okay. So how about if we try this for hydrogen gas at 17 degrees Celsius and 760 torr, right? Go ahead and give that a go on your own. You can pause here. So the variables that are changing here, it's 17 degrees Celsius instead of 25, and we're going to use torr to start with, right? So remember your R constants and the variables on your R constants. Go ahead and pause now if you want to give that a try. And if you give it a try, right, remember that 1 atmosphere is equal to 760 torr, right? So that's a relatively simple conversion. That means you can use the 0.0821 liters times atmospheres divided by moles per Kelvin. R constant, and if you don't recall, the molecular mass of diatomic hydrogen gas is about 2.015 grams per mole. So if you plug in all this information, plug and chug, you should come out to 0.0846 grams per liter, right? A much smaller density than our nitrogen gas. Okay, so up to this point, we've been talking about, we've been loosely talking about these scenarios with one type of gas present, or one type of molecule of gas present, right? So what happens if we combine multiple gases into the same container, right? If we make the assumption that all these gases behave ideally, we can apply Dalton's law of partial pressures, which essentially says just that the total pressure of a mixture of gases is equal to the sum of the partial pressures of all of those gases, right? So again, here we're assuming ideal gas behavior. So we're assuming low pressure, high temperature, minimal to no interactions between any of these gases. And if you look up here, right, so this illustration is meant to represent that one gas type exerts 300 kilopascals of pressure, another gas type exerts 450 kilopascals of pressure, and then this last gas type exerts 600 kilopascals of pressure. So if we take all those up, right, and we use our formula that Dalton's law, total pressure just equals the partial pressure of A plus P plus partial pressure of B plus the partial pressure of C, we get our total pressure, right? So you just simply add those all up, right? So 300 plus 450, 750 plus 600, 1350 kilopascals, right? So this is a simple, mostly simple addition problem depending on what you have to do in your problem. And we will try our practice problem on the next slide. Okay, so in order to use Dalton's law of partial pressure, we're actually going to go back and use some of the things we've learned about using the ideal gas law first, right? So our practice problem set up here on the left. Hit this and turn the volume off. Set up to the left here, right? So we have a 10-liter vessel that contains 35, or that is being held at 35 degrees Celsius, and it contains 2.5 times 10 to the negative third moles hydrogen, 1 times 10 to the negative third moles helium, and 3 times 10 to the negative fourth moles of nitrogen. I'm going to write these out in decimals instead of scientific notation in the problem. So above, right, we have total pressure equals the partial pressure of each of these gases, calculated using the ideal gas law, rearranged for P, and we are going to use our R constant of 0.0821 liters times atmospheres divided by moles times Kelvin, right? So we're going to set up our equation here, I hope. Oh boy. Okay, so we have our moles of hydrogen times our constant R times our temperature divided by our volume, right? And we're just going to do the same thing for the rest of our gases. So now we have our number of moles of helium and our number of moles of nitrogen. Again, these are being written in decimal format instead of scientific notation. And I haven't written out the components of the ideal gas law because it's identical for all of these, right? So our R value is always going to be the same. Our temperature is always going to be the same. And then our volume is also always going to be the same. So all you have to do is really plug in the thing that's different for each of these, which is the number of moles. Plug it in, cancel your variables, and then just plug and chug and work your way through the problem. So it looks like our video skipped forward here, right? So we have total pressure equals the partial pressures of each of these gases that we've calculated. And all we have to do after that is just add them together. So if I can get this video to work, that comes out to be 9.61 times 10 to the negative third atmospheres of pressure, right? So fairly simple and straightforward. The hardest part about this is identifying the variables that need to go into the ideal gas law for each of these different gases. Okay, so one other way you might see questions regarding Dalton's law are is through the use of molar fractions of gas. So this is an instance where we're still totaling the partial pressures of all gases present, but you may be given the number of moles of multiple types of gases and asked to calculate their molar fractions, and then use that information to figure out what partial pressure each different gas is actually using. So it's really not too complicated. We're going to walk you through one right now, right? So we have one vessel that contains 2.83 moles of oxygen and 8.41 moles of dinitrogen oxide, right? And so we're assuming ideal gas principles here. So these gases are not going to interact with each other. It's relatively low pressure. We're going to assume the temperature also fits the ideal gas law. So we're going to get going on that, right? So first thing we need to do is determine the total pressure, which will allow us to calculate the molar fractions of each of our gases. So we do this simply by adding up our pressures. So 2.83 plus 8.41 will equal 11.24 total moles. Excuse me, we're calculating total moles here, not total pressure. So to find the molar fraction of oxygen, we just simply divide 2.83 moles of oxygen by the total number of moles of gas present, right? And that's going to be 2.83 divided by 11.24. And then we'll multiply that by the total pressure of our vessel, right? So we're basically just determining the fraction of pressure that our oxygen applies to the total here, and we're doing the same for dinitrogen oxide over here. And then you just do 8.41 divided by 11.24, again, times your total pressure, which is 192 kilopascals. So if we divide 2.83 by 11.24, we determine our molar fraction of oxygen is actually 0.252, or 25.2%. Multiply that by 192, and just like that, we'll get our partial pressure exerted by oxygen, which is 48.4 kilopascals. If we do this for our dinitrogen oxide over here, looks like our video froze, 8.41 divided by 11.24 equals 0.748, or 78.4%. Multiply that by our total pressure, and there we have it. So we calculate our molar fractions by just dividing the number of moles of each gas by the total moles of total gases in our container, and then multiply that by our total pressure. So we know what portion of the pressure is exerted by both of our gases. Pretty straightforward. Now, right, so I've been hinting to this periodically throughout the past couple classes. Do you really think that all gases behave exactly the same? Right? Hopefully you're thinking to yourself, Well, not every gas is identical, so why would every gas behave exactly the same way, right? Which would be a good train of thought. So a few visual, visual representations of gases not behaving the same way are kind of shown here, right? So in our top cartoon, we have a dual vessel container here with a valve in the middle, right? And we have hydrogen gas on one side and oxygen gas on the other. Hydrogen gas being very, very small comparatively to oxygen. If we open the valve in between these two vessels, we see that the hydrogen gas initially fills the other container faster than oxygen fills its opposite container, right? And you might be thinking that this is diffusion of gases, but essentially as these two gases fill these two vessels at different rates, we would actually refer to this as effusion, right? So eventually they will reach equilibrium, and there'll be equal amounts hydrogen gas on the left and the right, as well as oxygen on the left and right, but the two gases do this at different rates, right? Which again is why we refer to this as effusion instead of diffusion. Here we have two different balloons, right? So one balloon is full of helium gas and the other is full of nitrogen gas, right? So if you see our before picture here on the left versus our after picture here on the right, we see that the helium balloon is actually shrank. And that's because the helium, which is much smaller than nitrogen, is actually bouncing around and finding its way out through the membrane of that balloon. And then one last cartoon here, right? Again, diffusion would be essentially the equal movement of all gases within a container. But in this container, if we place a divider in the center, and this divider has a hole, small relative to one of our gases, the smaller gas will effuse through that hole much faster than the larger gas. Right? So these are two visual representations of how not all gases behave exactly the same, right? Not all gases are identical in their size, polarity, or lack of polarity, and and they will also behave differently as you apply different temperatures and pressures to them, right? So this brings us to the kinetic molecular theory of gas, right? So you may have already been thinking about gases in this way, but this is really just to help put a stamp on that, right? So the kinetic molecular theory of gases essentially breaks down many of the rules we've been talking about and the way we've been describing how gases behave down to the idea that the things we're observing, measuring, calculating are all due to molecules of gas moving around, right? So the kinetic molecular theory of gas, or KMT, I will refer to it as from now on, basically has 5 principles, right? So the first, molecules move in a straight line unless perturbed, right? So you can basically see here in this container furthest to the left that these gas molecules are basically just bouncing around in straight lines, and they will continue in those straight lines until they hit a wall of that container, at which point they'll reflect off and bounce in a different direction in a straight line. Molecules are negligibly small compared to the space between them. So again, if you look at any of these images, these gas particles are meant to be very, very, very tiny compared to the empty space between all the gas molecules. And this goes back to that low pressure component of our assumptions to use the ideal gas law, right? Low pressure would assume not very many molecules or atoms of gas, thus few particles, very, very big space. The pressure exerted by a gas is due to the collisions from the molecules or atoms with a container's wall, right? So the fact that these gases exert a pressure on, say, this piston or the outside wall of a balloon is actually from all those molecules or atoms bouncing off of that wall at a very, very rapid rate, right? So as those gases hit something, they exert a force against it, and because it's happening so frequently, because these molecules are moving very, very fast, it causes pressure, right? An outward pressure. Molecules exert no attractive or repulsive forces, right? And another assumption of our ideal gas law is that these atoms and molecules don't ever interact with each other, and they don't perturb each other. And then the average kinetic energy is proportional to temperature in Kelvin, right? Essentially what that's saying is that the higher the temperature of a gas, the more kinetic energy those molecules have, right? The faster they're moving, the more pressure they're going to ultimately exert. So what does this look like back to some of our common gas laws that we've discussed, right? So Montan's and Charles' law, right, where heat increases energy and volume is constant, volume is constant as pressure increases. Boyle's law, where the smaller the volume under a constant temp, you can see over here. Avogadro's law, where increasing the number of particles will increase the number of collisions, far to the right here, right? So as we said previously while discussing Avogadro's law, if we double the number of moles, we essentially double the pressure. But if that pressure is allowed to expand, we'll actually double the volume of the container instead. And then Dalton's law goes back to large empty space and absolutely, air quotes, no interactions between particles allows the sum of partial pressures to equal that final pressure, right? And so those are, again, some of the assumptions we make when discussing the ideal gas law. So in the next few slides, we're going to discuss a few things that we would consider non-ideal behavior, right? What happens when we actually have a low temperature and a high pressure? Something that would decrease the space between molecules of gas and slow their kinetic energy. So one of the principles, right, of the KMT, and that we've discussed with our common gas laws, is that pressure is directly related to the kinetic energy of gas particles, right? And kinetic energy is defined as half times the mass of a particle times the speed squared. So the mass of a particle we can't change, but we can change their speed by changing things around them. So over here to the right, we have a graph of essentially the distribution of the speed of oxygen particles at a temperature of 300 Kelvin. So you can see we have an uneven or non-normal distribution of the speed of our oxygen molecules, where I guess you could say the majority of them are somewhere right around here at, say, 380 meters per second. But we have this other value here at roughly 500 meters per second, right? And so in the next slide, we'll talk about what RMS stands for. But the big takeaway here is that there's a non-normal distribution of the speed at which these gases or these molecules are moving in this container. So because of that non-normal distribution of oxygen molecules, in order to determine meaningful quantities of how these gases are behaving, we need to use a non-normal statistic to determine how fast these gas particles are moving, right? So we do that by taking the root mean square of our particles, and that's simply just the formula up here. I won't necessarily be asking you guys to use it. You should just know that, again, it's a statistic used for non-normal distribution of data. And again, we have non-normal distribution of the speed of our molecules here. And so over here in this chart to the right, we also see fractions of molecules of diatomic nitrogen gas and their speed as we heat them up. Right? So initially at 100 Kelvin, we see the majority of the molecules have a speed somewhere right around here of 250 meters per second. But again, we see that non-normal distribution where there aren't quite as many with a high speed as there are as a low speed, right? It doesn't break down to our normal Gaussian distribution. As we increase the temperature, we basically see that disparity increase, right? So we see continued non-normal distribution, but the fraction of molecules that are moving faster increases and increases. And at those really, really high temperatures, we see a whole array of speeds of those gas molecules. Now you might be thinking, right, in the previous two examples, we discussed examples of speeds of gases for the same molecule, right, oxygen versus nitrogen. Maybe you're wondering what happens with different molecules of gas, right? So one of the factors that we've discussed before, again, that is different between all gases and stops them from behaving exactly the same is their molar mass, right? So we can actually use molar mass to calculate the effusion rate of different types of gas, right? So we have Graham's law helps us explain the ratio of effusion rates. So we have effusion rate A of gas A divided by a fusion rate of B, gas B. And essentially what our equation here boils down to is the square root of the molecular mass of gas B divided by the molecular mass of gas A. And if we look over here again, so these are examples of different noble gases, all at the same temperature. And we can see that essentially as the molecular mass of each of our gases increases, right, helium, neon, argon, krypton, xenon, we actually see that their general speed slows. So even though they may all be exerting the same force or pressure, their speed is drastically different, right? And if one gas moves on average or root mean square faster than another gas, it will likely effuse at a different rate than another. So I guess just to reemphasize this, right? Even though these gases have different speeds, they have different masses, which allows them to exert the same pressure, right? So if you think back to physics, xenon has a much higher mass, but it's slower, so ultimately it carries the same momentum as a fast small particle like helium. So another way we can mathematically visualize or represent the behavior of gases and how they stray from how an ideal gas would behave is using the compressibility factor Z, right? So essentially we can use this formula. Z equals the molar volume of gas at the same temperature and pressure divided by the molar volume of an ideal gas at the same temperature and pressure, right? So basically what this breaks down to is the measured molar volume of any given gas versus what you would expect the molar volume of an ideal gas to be. So the closer Z is to 1, right, the closer your gas is to idealness. So we begin to observe differences in real gases versus ideal gases is as we compress them, right? So as more and more pressure is applied, the molar volume of a non-ideal gas is larger than we would expect. So here, again, 1 is, no matter what our pressure and temperature is, we could plug it into our ideal gas law, and we would have a molar volume of that ideal gas. But if we apply these pressures to real gases, and then take some measurements, plug in our molar volume of gas for those variables we've changed, right, temperature and pressure, we can plot our Z value. So for most gases here, except for hydrogen, which is very, very small, you can see that initially our gases are actually much more compressible than an ideal gas, right? So the molar volume is much smaller than what you would expect, right? Up to half with carbon dioxide. But then as we apply more and more and more pressure, we actually see that the molar volume of our gases is much, much larger or less compressible than our ideal gas. So depending on the variables that you have to control, at some point or another, our real gases will behave how we would expect them to in an ideal gas, but you'll notice that the variables or the things you can control that would cause these gases to do that differ gas to gas, right? So applying a pressure of somewhere between 200 and 250 atmospheres is when nitrogen behaves like an ideal gas. Somewhere over here, right around 400, is when methane and oxygen behave as a normal gas or an ideal gas. And somewhere around 500 pressures of atmospheres where CO2 would behave as you would expect it to if it was an ideal gas, right? So again, compressibility factor is one way we can mathematically measure and observe the differences in how real gases behave versus how they would if they were ideal gases. And the pressure increasing here is one of those key factors. So if you remember, right, the two things that are required to assume ideal gas behavior is low pressure and high temperature, right? So if we think back to the kinetic molecular theory of gases, what's actually occurring at low pressure and high temperature? Essentially at low pressure, right, we have very few gas particles in a very large space, and very high temperature means they're moving very, very fast, right? So under the ideal assumptions, we have those gas particles with a lot of space around them. The chances of them bumping into other gas molecules is very, very small, and they're moving very, very fast. if we start to change those things, right? So here our box goes from big to small, so we're increasing the pressure. Maybe we're taking away some of the thermal energy, so we're decreasing the temperature. We're actually going to cause an increase just simply in the probability of these molecules crashing into each other, right? So we're going to increase the number of collisions that occurs. As we increase the pressure more and more, the volume the molecules take up becomes much closer to the volume of the space they occupy, right? So in a theoretical sense, if we continue to squish down this square all the way until the point where it was about this big, our gas molecules would actually occupy all the space, would occupy all the space of that container, as opposed to in our ideal conditions where they essentially occupy very little to almost none of the space of their vessel. And also, as we lower temperatures, the kinetic energy of our molecules goes down, so they move slower, at which point the attractive forces between gases can actually interfere with their ability to move in linear directions, right? Essentially their behavior and directionality will be altered by those interactions with other gas molecules, which again, not ideal, but it is, more closely how it occurs in reality. So hopefully everyone remembers that I wouldn't say pesky. I mean, in the sense of an ideal gas behavior, pesky. But hopefully everyone remembers that intermolecular force that increases with the size of a molecule, right? So van der Waals or London dispersion forces increase as molecules become larger and larger, right? And this is actually another thing that can contribute to non-ideal gas behavior. So van der Waals, we see this here in our van der Waals equation, which takes into consideration the molecular attraction between molecules. So up here we have our ideal gas law, PV equals nRT, but we have the van der Waals equation, which actually takes into consideration things about our molecules, right? We know there's no true ideal molecule, so we have some correction factors here determined experimentally. So in order to correct for the pressure a real gas is exerting, we have to add in a correction for molecular attraction, right? Again, so you'll see here that the number of moles and the mass of the moles will affect the pressure they exert. And then over here, we have a correction factor for the volume our molecules also take up. Right, and then so like I said before when we discussed compressibility, somewhere between a very, very low pressure and a very, very high pressure in a small volume, Pivnert will apply, right? It varies gas to gas, whether that's nitrogen, methane, carbon dioxide, or oxygen. Pivnert will apply somewhere, but it varies from gas to gas because not all gases behave ideally. So again, this data is collected experimentally, so the data exists somewhere in tables, whether that's in your textbooks or other resources. But it's important to be able to use the van der Waals equation to determine the pressure of a gas, again, assuming non-ideal behavior of our gas. So we have a practice problem here. Feel free to pause now and work your way through it. But essentially all you're really doing is plugging in our correction factors from our table down here, from gas to gas, into our van der Waals equation up here, right? So the example here, we want you to calculate the pressure of a gas if it were ideal versus the actual pressure of a gas using our formula up here, right? So the example we're going to use is carbon dioxide. So go ahead, again, pause here, use Pivnert to calculate the pressure you would expect carbon dioxide to exert at in a vessel, 4.25 liters large. There's 3.46 moles of carbon dioxide, and that vessel is being held at 229 degrees Celsius, right? So go ahead and use Pivnert, calculate the value there, and then go ahead and use the van der Waals equation using our correction factors here, right? So 3.59 for A, and then 0.427 for B up here, right? And again, M is just moles of your gas. So go ahead and give that a try, calculate it out, pause. So you should have came up with roughly 33.5 atmospheres of pressure if carbon dioxide behaved ideally, versus 32.4 atmospheres of pressure using our experimentally derived correction factors here, right? And so why are they different? Because this pressure is not very high, the temperature is also not very low, and there is ultimately some attraction and some volume that these molecules of carbon dioxide take up. Again, in reality, there is no perfect ideal gas, so many of the assumptions we make when applying ideal gas laws don't hold true. Essentially, that's what boils down to here. Why are they different? Because they break many of the many of the criteria for the ideal gas law. So you can try this again here, right? So in this case, we have a flask that's 560 milliliters in volume, 21.3 grams of nitrogen. So you're going to have to do something with that in order to use PIVNERT and our van der Waal equation. And our container is being held at 145 degrees Celsius. You're going to have to do something to that also to plug the value in for temperature. So go ahead and calculate the ideal pressure using PIVNERT, and then the van der Waal pressure using the van der Waals equation, using your information here in our correction table. 1.39 for A, 0.0391 for B. Go ahead and pause and do that. So if you should have arrived at 46.562 atmospheres using PIVNERT, and about 46.594 atmospheres for the van der Waal equation, which are actually pretty close, right? But again, why are they different? Because ultimately, the pressure is not very high, temp is not very low, and there are some attractions between molecules of nitrogen gas, whereas under ideal conditions, we would assume there are none. All right, so if you have any questions, feel free to email me. Otherwise, I'll see you in our next class. And again, we will do more practice problems like this when we get to our in-class equations or in-class problems in a couple of weeks.